In this video, we're going to talk about graphing rational functions. And as we're in calculus class, this should be pretty much review. The main thing we want to make sure we understand when we look at rational functions is we know how to determine the domain and the asymptotes, vertical and horizontal asymptotes, as well as a possible whole. All right, so when we define a rational function is created by a ratio of polynomial functions. And a polynomial function is something that's quadratic or linear, cubic even. It is a long list of terms raised to a power, right? So I've got a sub n x to the n plus a sub n minus 1 x to the n minus 1. And of course, we don't want to have to write all of that, so we're going to abbreviate our definition and just say we have all of these terms that add up down to a constant term. And the polynomial in the denominator would look something very similar. I'm just going to use some different values for my constants, okay? So the first thing when we're thinking about a rational function is we want to think about the domain. And what we need to know is that the domain, when we're finding that, we know that the denominator is not allowed to equal 0. We have two pieces that are a subset of the domain, in a sense. When we think about our vertical asymptotes and our whole, those are going to be coming from those undefined values that we need to leave out of the domain. So whatever these undefined values are, they represent either a whole or a vertical asymptote. So when we start thinking about this, we always factor our numerator and denominator. All right, so factors that cancel, if we have a factor that cancels, and not always do we, but if we have a factor that cancels, that's going to represent a whole. And any factors that are left, and we'll say that are left in the denominator, those would represent a vertical asymptote. And any factor that is left after we may or may not cancel, but any factor that's left in the numerator, in the top of that, that's going to represent an x-intercept. So then we'll talk about the horizontal asymptote and the y-intercept. And y-intercepts are easy. We've been finding y-intercepts for a long time. In order to find a y-intercept, you're going to let x equal 0 and solve for the y value. All right, so now I'm going to pause and we'll talk about horizontal asymptotes and the comparison test after I erase. So for horizontal asymptotes, we're going to use the comparison test. And what the comparison test states is that we're going to compare the degree of the numerator n to the degree of the denominator d. Okay, so that n is coming from the numerator and the d is coming from the denominator. And what we say is if n is equal to d, then what we end up with is the horizontal asymptote is y equals a over b. So a being the leading coefficient in the numerator and b being that leading coefficient in the denominator. So this a and b value here, these two guys, are coming from that. And that occurs if the numerator is equal to the denominator. Now, if the degree of the numerator, if that n value is less than, if the degree of the numerator is smaller than the degree of the denominator. What we end up with is y equals 0, and that will always be the case. So again, we compare the degree of the numerator to the degree of the denominator, and if the numerator is smaller than the denominator, we end up with y equals 0. And the last situation here, if n, that numerator, is greater than the denominator, if the degree of the numerator is greater than the degree of the denominator, then we have y equals an oblique asymptote, or a slanted. Okay, so, and that is found, it's not a horizontal, it's a slanted asymptote. That's found using long or synthetic division. All right, so let's do one example. So here we're given a rational function. It's a ratio of two quadratic polynomials. We have x squared in the numerator and x squared in the denominator. And we need to list the attributes, and then we're going to graph this rational function. Of course, you have your graphing calculator handy. You just want to feel comfortable listing or knowing all of these attributes when you look at the function. So I'm going to factor both my numerator and my denominator. My numerator factors to x plus 6, x minus 1, and my denominator factors to x plus 6, x minus 3. All right, so if I ask you about the domain, you should pretty easily be able to tell me that x is not allowed to equal negative 6 or positive 3. Negative 6 coming from this factor, positive 3 coming from the other factor. So writing that domain in interval notation, x is in the set of all real numbers omitting negative 6 and positive 3, which looks like this. Negative infinity to negative 6, union negative 6 to 3, union 3 to infinity. Now, you'll notice we have a common factor in the numerator and the denominator, and that's going to reduce out or cancel. And because that cancels, x plus 6 cancels, we know there is a hole at x equals negative 6. So this negative 6 is that negative 6. It represents a hole. At this point, we have a reduced function. Okay? So we can think about f of x as being x minus 1 over x minus 3. And if I wanted to find the ordered pair for that hole, I would take my negative 6 and plug it into my reduced or smaller function. I can't plug it into the original function because the original function would give me 0 in the denominator, and that would be undefined. So, f of negative 6 gives me negative 6 minus 1 over negative 6 minus 3, which is negative 7 over negative 9. My hole occurs at negative 6, 7/9. So we have our domain, we have the ordered pair for our hole, and we have a reduced function that we are dealing with. Now, notice we have a factor left in the denominator, x minus 3. And what that tells me is that my vertical asymptote is going to occur at positive 3. So the vertical asymptote's a vertical line. We write that as the equation x equals a number, and in this case, that would be the number 3. X equals 3 is my vertical asymptote. So you'll notice negative 6 is left out of the domain, and positive 3 is left out of the domain. These two numbers represent either a hole or a vertical asymptote. Now, simply looking at this reduced version of the function, I could find my x-intercept. My x-intercept is going to come from that factor that's left in the numerator. My x-intercept is going to occur at 1. So I have 1, 0. And x-intercepts can be found by setting the function equal to 0. 0 equals x minus 1 over x minus 3. Cross multiply, you'll end up with 0 equals x minus 1 or x equals positive 1. But because we're so good at this, we can do that without a lot of additional practice. And then my y-intercept, the y-intercept occurs when I let x equals 0. So f of 0 equals 0 minus 1 over 0 minus 3. That's going to simplify to positive 1/3. And you see, negative 1 over negative 3, that would simplify to positive 1/3. Keep in mind, the y-intercept in a polynomial, quadratic, linear, cubic, etc., is always going to be that constant term. And since a rational function is a ratio of two polynomials, we're going to end up with that y-intercept being the ratio of the constants. In this case, the y-intercept is 0, positive 1/3. So we have one more attribute to list, or to make sure that we can identify, and that's going to be my horizontal asymptote. So continuing with this problem and considering our reduced function in order to find my horizontal asymptote, we have the function f of x equals x minus 1 over x minus 3. So what we do is we look at the degree of the numerator. There's a little invisible 1, so the degree of my numerator is 1, and the degree of my denominator is 1. And since n is equal to d, then my horizontal asymptote is going to be y equals a over b. And that a and b are going to come from the leading coefficients. In this case, we have a leading coefficient of positive 1 in the numerator and positive 1 in the denominator. So my horizontal asymptote would be at y equals 1 over 1, which simplifies to just y equals 1. So those are all of my attributes. And of course, to graph this, we can plug it straight into our graphing calculator, but here I'm going to consider our characteristics and graph it by hand. So just briefly, we have a horizontal asymptote at y equals positive 1, a vertical asymptote at x equals 3. We have an x-intercept at positive 1, a y-intercept at positive 1/3, and we have a hole at negative 6, 7/9, which is just below 1. So somewhere over here we have a hole. And we can see that this is going to create a curve down in the lower left side of our graph. And we could use points, or again, our calculator. We would determine that there would be another hyperbolic part of this curve in the upper right. Right? So that's what this rational function looks like, and that hopefully helps you with the review you need as we start talking about limits to infinity.